The term ANOVA stands for Analysis of Variance. The section introduces the concepts of one-way ANOVA by developing them in tandem with an example that runs the length of the section. This screencast will abbreviate some items in the section and will skip some of the terminology. The section should be read. The principal question that's addressed in the section is the true average cash register receipt different at two similar stores? The data consists of 5 randomly obtained cash register receipts from each of the stores. Here's the data. Here are the 5 cash register receipts from store 1. $88, $73, and so forth. Here are the 5 cash register receipts from store 2. $95, $101, and so forth. The answer to the question of whether the true mean cash register receipts are different at the two stores follows from completing the one way of analysis hypothesis test. Here's the 5-step hypothesis test. The first step is stating the null and alternative hypothesis. In this case, the null hypothesis is mu1 equals mu2. That is, the population mean cash register receipt at store 1 is the same as the population mean cash register receipt at store 2. The alternative hypothesis says the population mean cash register receipts are different at the two stores. Note that the null and alternative hypotheses are always about population parameters, about mu's in ANOVA, not about sample statistics like X bars. Step 2 involves choosing a significance level. We'll choose alpha equal 0.05. The upper bound on the probability of a type 1 error has been set at 5%. That is, we've limited the probability of incorrectly choosing H1, or if you wish, the probability of incorrectly deciding that the population mean cash register receipts at the two stores are different. Step 3 of the hypothesis testing method requires 3 things. Now, I know you're not going to know what all of these things mean yet. We will be developing those over the next several pages. But let's go over the 3 things that are required. The first thing that's required is a statement of the model assumptions. In one-way analysis of variance, the model assumptions are sampling is independent and random. Sampling is from normal populations. The normal populations have equal variances. That's the first thing that's required, the statement of the model assumptions. The next thing required is a statement of the test statistic. The test statistic in the case of one-way analysis of variance is MSA over MSW. And the final thing that's required is a statement of the distribution of the test statistic, and in one-way analysis of variance, that distribution is an F statistic, and in this case, with 1 degree of freedom for the numerator and 8 degrees of freedom for the denominator. Now, what our test statistic is going to measure, and as I said, we'll see this a little bit later, what it's going to measure is how much variation there is amongst sample means, and it's going to compare it to the amount of variation there is within the individual samples. When there's a lot of variation amongst the sample means, compare it to the amount of variation within the individual samples, that makes this test statistic large, and in fact, a lot of variation amongst the sample means is in fact evidence of H1 being true. The two population means are different. Step 4 is about doing the computations. As we move through step 4, we'll introduce more about the test statistic, about the probability distribution, and about the model assumptions. So, bear with me a bit and let's go over some of the computations that are necessary to get to the point to define the test statistic. Here are the 5 cash register receipts from store 1 repeated. Over here are the 5 cash register receipts from store 2 repeated. I went ahead and calculated the sum of the 5 cash register receipts from store 1, and I've gotten $400. And then I computed the mean cash register receipt for those 5 receipts from store 1. 400 divided by 5 is $80. Just to make sure we're all on the same wavelength here, I've left spaces for you to complete the same calculation, the total of the 5 cash register receipts for store 2, and then the mean, the sample mean cash register receipt from store 2. Another mean we're going to use is the grand mean. What the grand mean is simply the mean of all 10 of the cash register receipts together. So if you add up all 10 of the cash register receipts and divide by 10, you get the grand mean, and in this case, that's $90. Here is a scatter plot of what we've seen so far. The vertical axis is a dollar axis. Here are the store 1 receipts, the 5 receipts. Here are the store 2 5 receipts. Here's the grand mean, $90. Here's the sample mean of the store 1 receipts, $80. Here's the sample mean for the store 2 receipts, the one that you computed above, of $100. Now, if we looked at this from an intuitive standpoint, that is, we're wondering whether the population mean cash register receipts from the 2 stores are different or not. Certainly there's some difference. There is difference between these sample means. That would seem to say there's a good chance that the population means would be different. But you know, these cash register receipts from store 1 are overlapping with these cash register receipts from store 2. Are these up here kind of just by chance that they came out of store 2, and maybe a few of these down here just by chance that they came out of store 1? It's not clear by looking at that scatter plot whether or not the true means, the true population means, are actually different. Now let's develop some measures of variation that will allow us to construct a test statistic that in turn will allow us to do a statistical test and allow us to determine whether we can say that the population mean cash register receipts are different at the 2 stores without taking more than a 5% chance of being wrong. The first measure of variation that we're going to develop is SSA, the sum of squares among sample means. What SSA measures is the amount of variation that exists among the sample means. So what it's going to do is it's going to take, to begin with, the first sample mean, compare it to the grand mean, square that difference, and then multiply it by the number of observations, in this case, in the first sample. So let's go through that calculation for the first sample, and then I'm going to let you go through that calculation by yourself for the second sample. And then to get SSA, you simply are going to add the two totals here, and the sum of those two totals will be the SSA quantity, the total amount of variation there is amongst sample means. So, to start the calculation, there are 5 observations in the first sample. The first sample mean was 80. The grand mean was 90. 80 minus 90 squared, 80 minus 90 is minus 10, squared is 100, times 5 is 500. Now, you go ahead and you can figure this one out, and if you really need to, you can pull down that text box and find out what the answer is. And also, you're going to want to add the 500 that you get from the first sample to whatever you got over here to get the total. And that'll give you SSA. The next measure of variation, SSW, it's the sum of squares within samples. It measures the amount of variation that exists within all the samples. Now we're going to use some notation that looks complicated, but it really isn't particularly. Xij. What Xij represents is it's the ith observation in the jth sample. Like, for example, X52 would represent the 5th observation in the second sample, and if we look up here, well, I guess we'd have to look at a list. Let's see, if we look up here, there it is. The 5th observation in the second sample is 105. So, computing SSW, our measure of how much variation there is within the samples, it says take every sample observation in the first sample, subtract off the first sample mean, take that difference and square it, and add it up over all 5 observations in the first sample. So I'm not going to scroll up further again, you can go back and check, but the first observation in the first sample was 88 minus the first sample mean 80. So far we've got 8. Squaring that, because it says to square it, we get 64 plus 73 minus 80. So what is that? Minus 7 minus 7 squared is plus 49. So we've got 64 plus 49 and so forth going across here. And when we add them all up for the first sample, our amount of within group or within sample variation is 412. And I'm going to ask you to do that for the second sample. The second sample mean, you were supposed to have computed it up there, is 100. And so you'd go down the observations in the first sample, 95 minus 100 squared plus 101 minus 100 squared, and so forth. Go ahead and make that computation. Then add these two things up and get the sum of squared within sample variation, the SSW number. If SSA, which measures the amount of variation there is between sample means, is much larger than SSW, which measures the amount of variation there is within the individual samples, then that would be evidence that in fact the population means are different. But we're not through yet. It would be a good place, however, to do homework 1, problem 4. In fact, let's put in another screencast. When you're ready to restart, click on the screencast at the top of the next page.